Welcome, everyone. I am Lin Yen Jen from the National Center for High Performance Computing. Today, I'm pleased to share our work on privacy-preserving pathology AI, enabled by high-performance computing and federated learning. Our infrastructure addresses NMIUC staging, grading, and BCG recurrence risk. By utilizing NVIDIA Flare and the FedAV algorithm, we aggregate model updates across heterogeneous sites, KMUH on TWCC and VUSHK on local GPU servers. Importantly, all whole slide images remain securely behind local institutional firewalls, ensuring complete privacy. Why focus on NMIUC? While conventional staging and grading guide care, recurrence risk remains highly heterogeneous. Over 30% of patients treated with BCG immunotherapy still experience recurrence. Our pipeline translates digital morphology into actionable risk stratification, directly filling this clinical uncertainty gap while respecting data boundaries. To achieve this, our compute pipeline targets three key tasks from a single WSI feature extractor: supervised stage classification, supervised grade classification, and unsupervised relapse-free survival clustering. By linking these morphological representations, the model learns the underlying connections between diagnostic histology and actual clinical recurrence risk. Moving AI to the real world reveals a severe domain shift. VUSHK uses Leica scanners at 20x, while KMUH uses Hamamatsu scanners at 40x. Local models perform beautifully on internal data, but degrade sharply on external tests. This highlights why federated training is essential to build truly robust representations. Our primary objective is to make whole slide image learning robust across diverse real-world institutions. By establishing secure, distributed training across heterogeneous GPU environments, we aim to deliver generalizable models for stage, grade, and fusion risk without centralizing private clinical data. Technically, the federated learning loop operates through NVIDIA Flare. KMUH and VUSHK train local models independently, keeping their slide data locked locally. Every epoch, only model weights are transmitted to the central server for FedAV aggregation, utilizing strict whitelist IPs to maintain absolute data security. Our model pipeline begins with patch extraction and magnification normalization. We freeze a Dino V2 backbone to extract features, then train parallel CLAM branches to predict stage and grade. Finally, we fuse these embeddings, reduce their dimensions, and apply a Bayesian-Gaussian mixture model to cluster patients into distinct recurrence risk groups. Our experiments leveraged a large cohort of over 1,400 retrospective cases. This involved VUSHK's site with over 1,000 cases on local A4000 GPUs and KMUH's cohort on Taiwan's TWCC cloud using V100 GPUs. Together, they form a highly realistic testbed of diverse clinical populations and computational setups. The results demonstrate that federated learning significantly boosts cross-site robustness. We achieved 86% accuracy for stage and 79% for grade. Crucially, federated learning closed the performance gap, outperforming single-site models by up to 13% on external testing without ever sharing a single patient image. Most remarkably, our compute-derived fusion risk factor successfully stratified relapse-free survival. In the VUSHK cohort, the hazard ratio reached 2.7, outperforming traditional stage at 1.9. We observed a similar strong prognostic signal in the KMUH cohort, proving our morphological representations carry powerful, clinically actionable prognostic value. To translate this into clinical practice, we must address both validation and FL operations. While our model captures rich morphological signals without genetic data, real-world deployment requires robust IT security, whitelisted connections, and adaptation to clinical workflows, along with expanded validation across broader non-papillary tumor cohorts. In conclusion, clinical AI deployment is fundamentally a compute and coordination problem. By combining high-performance computing, secure federated learning, and cross-site collaboration, we have demonstrated a scalable path to build robust, privacy-preserving diagnostic models. This established architecture lays the groundwork for connecting more clinical sites to improve patient outcomes globally.